welcome to the Crazy Hat Chemist. So another video here today in atomic structure and electron configurations. So let's get moving. Bam! Today we are talking about the Pauli Exclusion Principle. We are also going to do the electron configuration of helium and the orbital box diagram for helium, as well as the 4 quantum numbers associated with each electron in helium. So, Pauli Exclusion Principle. For multi-electron atoms, that is anything past hydrogen, no 2 electrons can have the same set of 4 quantum numbers. That is N, L, M sub L, and M sub S. Remember, the N, L, M sub L, and M sub S, the 4 quantum numbers, is a unique address for every single electron in an atom. And the Pauli Exclusion Principle says no 2 electrons can have the same set of those 4. So, let's do the electron configuration for helium. It's the atomic number of 2. That's a Z of 2. So we're going to write the symbolic notation, the standard notation of helium, standard nuclear notation. That is AXZ. And we have the Z of 2. That tells you that the atomic number is 2. That tells you that the number of protons is 2. That tells you that the number of electrons is 2. Helium is neutral, so therefore 2. Okay, so we're going to write out the electron configuration for helium, and that is a 1s2. That is not read as 1s squared. That is read as 1s2. Okay, so just like before, that 1 corresponds to the principal quantum number that's in the blue there. That's a 1. And the L is the angular momentum quantum number. That is an s-type orbital. That's an L of 0 in this case. And there are 2 electrons, as the Z is 2. Hopefully that works for you. Now, here are the possibilities. There are 3 different possibilities in which to write out the orbital box diagram for helium. So, I got a box. I'm going to label the box as a 1s. Okay, remember, you can fit a maximum of 2 electrons in an orbital, that is in a box. Okay, so first electron is up. It's always up by convention. The first electron is always up by convention. Okay, and the second electron, we're going to say it's up. So we're going to write out the total number of quantum numbers for each electron. So this first electron on the left-hand side has an N of 1, an L of 0 because it's an S-type, an M sub L of 0 because it's in a single box, and then an M sub S of plus 1/2. The second electron, an N of 1, L of 0, M sub L of 0, all those work well. And then the M sub S is plus 1/2. Now, you should see that all 4 of those quantum numbers are the same. So, this violates the Pauli Exclusion Principle, so this is wrong. This orbital box diagram is incorrect. This will not work. So, we're going to do another possibility. We got a box, we got our 1s labeling of that particular box. We're going to put an electron in that box. We're going to put this one down now this time. Okay, by convention, that doesn't normally hold true, but we're going to fly with this. Well, our next electron is going to be down as well. Okay, and then we're going to label these. That first electron on the left-hand side is an N of 1, L of 0, M sub S of, M sub L of 0, and an M sub S of negative 1/2 because that electron is facing down. Now we're going to label the 4 quantum numbers associated with the second electron on the right-hand side. N of 1, L of 0, M sub L of 0, and an M sub S of negative 1/2. You should see that all 4 quantum numbers are the same, and it is truly in the same region, and that is the M sub S value, and that is a violation because you cannot have the same set of 4 quantum numbers be the same for any electron in an atom. Now, you should see that both of these examples I've either had the electrons upwards facing or downward facing within that box. Okay, and I've highlighted in the red circle with the line through it the part that does not work. The part that does work is the N of 1. That is absolutely there because the blue principal quantum number of 1 in 1s2, the 1 in 1s2 is an N of 1. So you can't change that. The type of orbital in which this is in is an s-type orbital, and that s-type orbital corresponds to an L of 0, so you cannot change that either. Okay, the box labeling of the s-type orbital where those electrons are is a 0. So the m sub l value is a 0. So you cannot change that. The only parameters of which you can change are the arrows and their orientation. So let's do the correct one, and hopefully you have an idea of what the correct one should be with some of the hints that I've given you already here in this example. So we got a box. We got our 1s box labeling, so that is all correct. We're going to have an upwards facing arrow here, but because by convention, the first electron, the first arrow is an upwards facing arrow, has always been that way. Okay, now we're going to write out the set of quantum numbers to represent that. And our second electron is going to be a downwards facing arrow. Okay, now these are anti-parallel to one another. That means that these electrons are going in opposite spins. One is clockwise, one is counterclockwise. Now, here are the set of 4 quantum numbers to represent the left-hand electron. N of 1, L of 0, M sub L of 0, M sub S of plus 1/2 because it's facing up. Now you should see that the first 3 quantum numbers, N, L, and M sub L, are correspondingly the same for all of them, even the ones that had violations in them. So you know that is correct. Now the right-hand arrow is here. And then it's an N of 1, an L of 0, an M sub L of 0, and an M sub S of negative 1/2. That one right there is correct, because you have a set of 4 quantum numbers that differ. Even though it differs in one aspect, it still differs for each electron in an atom. Okay, so that is the correct way to write out the orbital box diagram for helium. So that one is correct. That is defining the Pauli exclusion principle there with that problem. Go over that. Make sure you understand the Pauli exclusion principle, because that is a great vocabulary question. Okay, that was another crazy hat video by the Crazy Hat Chemist, and whoa, I got some crazy hair here today. Okay, oh, by the way, at one point in time, I just had crazy hair, and that's how this all started, and I used to dye my hair. Now, well, I don't have much hair anymore, so I'm left to doing hats. So give me a thumbs up if you like that video, subscribe to my YouTube channel, and I will see you next time for some more cool chemistry videos. See you later. Bye now.